So let's look at the easiest part of ViT, or the easiest building block of ViT, that's layer normalization. And layer normalization is pretty straightforward. We can see the formula on screen. It's pretty simple, but it's essentially scaling. But we need to understand that there is certain intuition behind that scaling, and it's not just randomly scaling it. And why do we do the scaling, and how is it different from batch normalization? So before we go to the formula and the code and all that, let's go to a simple example. Let's try to understand what is the intuition behind layer normalization, right? So let's say we have a data set which consists of x and y, where x is the input and y is the labels. Now x is 1, 2, 3, 4, 5, 6, etc. Y is 2, 3, 4, 5, 10, 12, 14, and 16, right? So now if we write a function that maps y to x, this function will also be something like where f is equal to x plus 1, where x is less than 5, and 2x when x is greater than or equal to 5. And that's pretty simple. From the dataset itself, we can see that relationship, and it's pretty straightforward. There's nothing too confusing here. Now we want a neural network to learn this. We want a neural network to approximate to this function. Essentially, neural network is a function approximation algorithm, right? So we make a simple neural network with the first layer having 4 neurons, the second layer having 2, and there's one in the output layer. Each of these layers have its own weights, W1, W2, and W3. Let's go through a training iteration, and let's see what happens to the inputs and the labels and the loss, and let's see why we need layer normalization to help us in a situation like this. Before we do that, we know that the output is directly dependent on the weights, that is W1, W2, and W3, and the loss is directly dependent on the output. And so in a way, the loss is dependent on the weights, that's W1, W2, and W3. And if the loss updation is drastic, then the weight updation will also be drastic, because if there's a huge change between the loss in a certain iteration and the loss in the next iteration, then the weight updation which will accompany the back propagation of this loss will also be huge, right? So let's look at an example. Here, for the first step of the epoch, we have 1, 2, 3, 4 coming in, and it gets forward propagated, and finally we have an output. Now this output will be a list, but this output and this label together, we can calculate a loss, and we can back propagate it. Now, let's say this loss causes a weight updation of W11 in the first layer during its back propagation, right? The second layer here, that is the layer W2, expects the outputs from the first layer to be in a certain range, right? And after the first iteration, this range gets changed by a small amount of delta W11, right? But what happens in the second epoch is that when 5, 6, 7, 8 comes in, and this gets forward propagated, and we calculate the output. Once we have the output, we can calculate the loss between this output and this label, and this can then be back propagated, right? This causes a weight updation of W12. So this is the weight updation of the first layer in the second step. Now, let's take a condition where W12 is much higher or much lower. It can be any of these two than the first one, right? What happens? So the first thing we need to understand is that once this entire thing back propagates, that will also be subtracted here for obvious reasons. Because that is the weight updation which belongs to that certain layer. So now this entire thing is the new range, right? Now, when a new input comes to this model, what happens is that W2 does not recognize the new range. That is this entire thing. So the new inputs coming in as something which W2 cannot recognize, or W2 is not tuned or optimized for. So it can give wrong outputs, or it can give outputs which are not, let's say, advantageous for the model. This causes the output to be very different, which in turn causes the loss to be very different, which in turn causes another weight updation here. and this chain keeps on going, and this is not good for convergence, right? We want our model to converge as fast as possible and as smoothly as possible. This also affects the smoothness of convergence a lot when we have such magnitude explosions or such rapid range changes. This is where we use layer normalization, where we scale down the outputs of a certain layer to a certain range, where the next layer is never surprised by the outputs coming out from the previous one. So the, here in the example which we have, W1, 2 can definitely be much higher or much lower than W11. The reason for that is because if you look at the functions, right, we can clearly see that for the first batch, the function that governs the output, and for the second batch, the function that governs the output are very different. So the weight updations can be very different. So in a situation like this, when we have rapid weight updation because the data set has a lot of variance in it, as the data points in the data set are very highly different from each other. In situations like that, this kind of scaling will help us a lot in preserving the range of outputs that can come out from a certain layer. Let's try to understand what layer normalization is. Layer normalization is pretty simple. I'll just write down the formula. So let's say we have xi as an input. So how we scale it is we subtract the mu, that is the mean. So the mean of xi gets subtracted, divided by sigma, which is standard deviation, as a standard deviation of the same tensor xi, and an epsilon. So the epsilon is a very small number, that is like 10 power minus 6 or 10 power minus 4 or something like that. And this becomes xi cap. Now, the final output yi, that is the layer normalized output of xi input, is gamma xi plus beta, where no points for guessing, but gamma and beta are parameters of the model. So they are trainable parameters. So you can think of this formula as compressing xi, but allowing the compression to be learned. So in a way, we are learning how to compress this, how to not compress, how to scale the data into a certain range. And essentially, this is learned scaling in a way. And that's for the theory. We can actually move on to the code. The code is pretty simple. This is the code, and we can see that it's inherited from nn dot module, obviously, so that we can back propagate and do all those things easily, and we don't need to write code for that, because the main idea of the video is to learn how these functions work intuitively. So in the init function, we declare epsilon and we declare alpha and beta. So instead of gamma, I just wrote alpha in the code. You can change it to gamma if you want, it's completely fine. And below, in forward, we have, it's pretty simple. Numerator is x minus x dot mean, and dimension is set to -1 because we don't need to apply the normalization in the batch dimension. We want to apply it in the dimension which has information that is coming out from the previous layer. So this is the last layer, and the last layer essentially will, for the most part, be your information layer. So we do a mean across that and we subtract that from x. And for the denominator, it's just a math dot square root of standard deviation of x plus epsilon, and epsilon is set here, or we have set a default value of IE minus 6. That's the same value which is given in the paper as well. Now we just return numerator by denominator into self.alpha plus self.beta. Self.alpha is an n dot parameter and self.beta is also an n dot parameter. The only difference is the initialization. Since alpha since alpha or gamma in the image is something that is going to be multiplied, we initialize it with ones. And since beta is something that's going to be added, we initialize it with zeros, since it can be learned later and it can essentially add or subtract or whatever it needs to do, right? So this is for the theory and the uh, practical coding of the concept. I hope you understood this, and it's a very good topic to know and use when you're building custom models, when you're trying to make your model converge, and especially it's very useful when you're working with transformers, since layer normalizations are essentially a part of its fundamental architecture. So yeah, that's pretty much it for the video.